Welcome! Today we are going to learn about something called a Venn diagram. And I want you to know right from the start, this is not going to be rushed. We are going to go through everything slowly, carefully, and together. So take a breath, settle in, and let's begin. The name of what we are learning today is Understanding Venn Diagrams. The full title is Understanding Venn Diagrams, a systematic introduction for absolute beginners, illustrated through Ikigai. And the key word I want you to hold on to from that title is beginners. This is made for you exactly where you are right now. No prior knowledge needed whatsoever. So, what is a Venn diagram? Let's start with the formal definition, and then we'll unpack it together word by word, because it sounds a little intimidating at first, but I promise it becomes very natural. Here it is. A Venn diagram for n sets partitions the universe into 2 to the power of n regions, where each region corresponds to one possible pattern of membership and non-membership in those sets. Okay, let's slow down and talk about what every part of that actually means. First, what do we mean by n sets? Think of a set as simply a collection of things. A group. A bunch. You could have a set of your favorite foods. A set of even numbers. A set of days that start with the letter T. Anything. N is just a stand-in for however many sets we happen to be working with. If we have 2 sets, then n equals 2. If we have 3 sets, then n equals 3. Now, the word universe. In everyday life, the universe means everything that exists. In mathematics, we use the same word, but we get to define it ourselves. The universe, which we often just call the universal set, is the complete collection of all the things we are considering in a given problem. Everything relevant lives inside the universe. Now, partitions. To partition something means to divide it into separate, non-overlapping pieces, where every single part of the whole belongs to exactly one piece. Imagine cutting a pizza into slices. Every bit of pizza belongs to one slice, and no part of the pizza is shared between 2 slices. That's a partition. So a Venn diagram divides the universe into separate, non-overlapping regions. And how many regions? 2 to the power of n. Let's think about what that means with a few quick examples. If n equals 1, meaning we have just one set, then we get 2 to the power of 1, which is simply 2 regions. If n equals 2, we get 2 to the power of 2, which is 4 regions. If n equals 3, we get 2 to the power of 3, which is 8 regions. The number of regions always doubles every time we add one more set. And each of those regions corresponds to one possible pattern of membership and non-membership. What does that mean? It means that each region answers a specific combination of yes or no questions about belonging to the sets. Is this element inside set A? Is it inside set B? Every possible combination of yes and no answers gets its own dedicated region in the diagram. That is the beauty of a Venn diagram. It's exhaustive. Nothing gets left out. Now there is something very important I need to tell you, and it comes with a name, the golden rule. The golden rule is this. A formal Venn diagram must have exactly 2 to the power of n distinct regions. Every single combination of membership and non-membership must be physically visible and present in the diagram. Even if a particular region turns out to be empty, meaning no actual elements live there, the region must still exist as a visible area. It must still be drawn. Now, this raises an interesting question. What do we call a diagram that looks like a Venn diagram but skips the empty regions? What if someone draws a diagram that only shows regions where actual elements exist and leaves out the empty ones? That type of diagram has a different name. It is called an Euler diagram. Named after the mathematician Leonhard Euler, an Euler diagram is more casual and practical. It only draws what's non-empty. A formal Venn diagram, on the other hand, is strict and complete. It draws every possible region, empty or not. Both are useful, but they are different things. And now you know the difference. Let's now talk about how we actually read and describe the regions in a Venn diagram. This is where a very elegant and systematic idea comes in: binary membership codes. Each element, each thing, can either be inside a given set or outside it. There is no in-between, and we represent those two possibilities with numbers. If something is inside a set, we write a 1. If something is outside a set, not a member of it, we write a 0. Inside equals 1. Outside equals 0. Now, to guarantee that we find every single one of the 2 to the power of n distinct regions without missing any, we can be completely systematic. We construct what is called a truth table. This is just a structured way of listing out every possible combination of 1s and 0s. For any location in our diagram, we ask a sequence of yes or no questions, one question for each set, and we record the answers as ones and zeros. Let's make this concrete with an example of n equals 3. So we have 3 sets. Let's call them set A, set B, and set C. For any point or element in our diagram, we ask 3 questions. Question 1. Is it inside set A? If yes, write 1. If no, write 0. Question 2. Is it inside set B? If yes, write 1. If no, write 0. Question 3. Is it inside set C? If yes, write 1. If no, write 0. Now we write those answers as a 3-digit code. For example, the code 101 means, yes, it's in A. No, it's not in B. Yes, it's in C. And that specific region, the region with code 101, corresponds exactly to a mathematical intersection. Specifically, it is A intersect B, complement intersect C. Let's say that in plain English, the region that belongs to A and does not belong to B and belongs to C. The code 101 captures all 3 of those conditions simultaneously. This idea of using binary codes to systematically label every region is the engine that makes Venn diagrams rigorous and complete. Now let's look at the simplest possible case, just one single set. So n equals 1. When n equals 1, we get 2 to the power of 1 regions, which equals exactly 2 regions. Just 2. The universe is divided into 2 parts. Let's build a little table. We have one set which we'll call set A, and we ask our one question, is the element inside A? If the answer is no, if the element is outside A, we write the code 0. And the mathematical name for everything outside of A is a complement. The complement of a set is everything in the universe that is not in that set. If the answer is yes, if the element is inside A, we write the code 1. And mathematically, that region is simply called A itself. So the 2 regions are the region coded 0, which is A complement, everything outside A, and the region coded 1, which is A, everything inside A. Visually, picture a large rectangle representing the entire universe. The universal set, often labeled with the letter U. Inside that rectangle, there is a single circle. Everything inside the circle is region 1. That's A. Everything inside the rectangle but outside the circle is region 0. That's A complement. Simple, clean, and complete. 2 regions, exactly as promised. Now let's make this real with an actual, concrete example. Still one set. N still equals 1. Let's define our universal set. The universal set U is the collection containing the numbers 1, 2, 3, 4, and 5. Just those 5 numbers. That is our entire world for this problem. Now let's define set A. Set A is the collection of even numbers from our universal set. So A contains 2 and 4. Just those 2 elements. Now let's ask, where does everything go? The numbers 2 and 4 are inside set A. They are even, so they belong there. They live inside the circle in our diagram. The numbers 1, 3, and 5 are not even, they don't belong to A. So they live outside the circle but still inside the large rectangle, because they are still part of the universe U. So in our diagram, inside the circle we see 2 and 4. Outside the circle but inside the rectangle we see 1, 3, and 5. And that is our complete, valid, 2-region Venn diagram for one set. Every element of the universe has a home. 2 and 4 live in A. 1, 3, and 5 live in A complement. Nothing is missing. Nothing overlaps. The partition is perfect, and that is where we'll pause for now. Now we are ready to take the next step. We are going to add a second set. And as we do, I want you to notice how everything we already learned carries forward perfectly. The logic is exactly the same. We're just asking one more question. 2 sets, so n equals 2. And 2 to the power of 2 gives us 4 regions. 4 distinct areas, each representing a unique combination of membership answers. Let's build our truth table together, nice and slowly. We have 2 sets this time, set A and set B. For any element or location in our diagram, we ask 2 questions. Is it inside A? Is it inside B? We record the answers as a 2-digit binary code. Let's go through all 4 possibilities. The first row, the answer to both questions is no. 0 for A, 0 for B. The code is 0, 0. In mathematical language, this region is called A complement intersect B complement. In plain English, everything that is outside A and also outside B at the same time. This is the outermost region. elements that don't belong to either set. The second row, no for A, yes for B. The code is 0, 1. Mathematically, this is A complement intersect B. In plain English, things that are not in A but are in B. Only in B, not in A. The third row, yes for A, no for B. The code is 1, 0. Mathematically, this is A intersect B complement. Things that are in A but not in B. Only in A, not in B. The fourth row, yes for both. The code is 1, 1. Mathematically, this is A intersect B. Things that belong to both A and B simultaneously. This is the overlap, the region in the middle where the two sets share members. Now let's picture the diagram. Again, we have a large rectangle, our universe U. Inside the rectangle, we have two overlapping circles. The left circle represents set A. The right circle represents set B. The region that belongs only to the left circle, inside A but outside B, that's the 1, 0 region. The region in the middle where the two circles overlap, inside both A and B, that's the 1, 1 region. The region that belongs only to the right circle, inside B but outside A, that's the 0, 1 region. And the region inside the rectangle but outside both circles entirely, outside A and outside B, that's the 0, 0 region. 4 regions. Every possible combination accounted for. The diagram is complete and valid. Now let's put real numbers in and make it fully concrete. Our universal set U is the collection of numbers 1, 2, 3, 4, 5, and 6. 6 elements total. That's our entire world. Set A is the collection containing 1, 2, and 3. Set B is the collection containing 3, 4, and 5. Now let's figure out where each element lives. Start with the number 3. Is 3 in A? Yes. 3 is listed in A. Is 3 in B? Yes. 3 is listed in B. So 3 belongs to both sets. It lives in the overlapping middle region, the 1, 1 region. 3 is the shared member. Now the numbers 1 and 2. Is 1 in A? Yes. Is 1 in B? No. So 1 belongs to A but not B, the 1, 0 region. Same for 2. 2 is in A but not in B. So 1 and 2 both live inside the left circle only. Now the numbers 4 and 5. Is 4 in A? No. Is 4 in B? Yes. So 4 belongs to B, but not A, the 0, 1 region. Same logic for 5. 5 is in B, but not in A, so 4 and 5 live inside the right circle only. Finally, the number 6. Is 6 in A? No. Is 6 in B? No. 6 doesn't belong to either set. So 6 lives outside both circles, but still inside the rectangle, the 0, 0 region. 6 is in the universe, but it's not claimed by either set. Let's take stock. In the left circle only, 1 and 2. In the overlapping middle, 3. In the right circle only, 4 and 5. Outside both circles, 6. Every element of the universe has exactly one home. The partition is perfect. 4 regions, all accounted for. Now let's go one step further. 3 sets, so n equals 3, and 2 to the power of 3 gives us 8 regions, double what we just had. This is where things get beautifully rich, but also where the systematic binary code approach really earns its keep. Without a truth table, it would be easy to accidentally miss a region. With it, we're guaranteed to find all 8. We have 3 sets now, A, B, and C. For any element, we ask 3 questions. Is it in A? Is it in B? Is it in C? 3 questions, 3 answers, each a 1 or a 0. Let's walk through the entire truth table, row by row. Row 1, 0, 0, 0. Not in A, not in B, not in C. This is A complement, intersect B complement, intersect C complement. Everything outside all 3 sets. Row 2, 0, 0, 1. Not in A, not in B, but yes in C. This is A complement intersect B complement intersect C. Only inside C and nothing else. Row 3, 0, 1, 0. Not in A, yes in B, not in C. This is A complement intersect B intersect C complement. Only inside B and nothing else. Row 4, 0, 1, 1. Not in A, yes in B, yes in C. This is A complement intersect B intersect C. Inside B and C, but not A. Row 5, 1, 0, 0. Yes in A, not in B, not in C. This is A intersect B complement, intersect C complement. Only inside A and nothing else. Row 6, 1, 0, 1. Yes in A, not in B, yes in C. This is A intersect B complement intersect C. Inside A and C, but not B. Row 7, 1, 1, 0. Yes in A, yes in B, not in C. This is A intersect B intersect C complement. Inside A and B, but not C. Row 8, 1, 1, 1. Yes in A, yes in B, yes in C. This is A intersect B intersect C. Inside all three sets, simultaneously. The very center. 8 rows. 8 regions. Every combination of 3 yes or no answers is represented exactly once. Now let's picture the diagram. We still have our large rectangle for the universe. Inside, we now have 3 circles, each pair of circles overlapping with the others, and all 3 meeting at a central point. The arrangement looks like a classic 3-circle Venn diagram, which you may have seen before. Each of the 8 regions we just described corresponds to a distinct area in this figure. The outermost area, outside all 3 circles, is 0, 0, 0. The very center, where all 3 circles meet, is 1, 1, 1. And every region in between corresponds to exactly one of the 6 remaining codes. Let's now bring in a concrete example for 3 sets to make all 8 regions visible with actual numbers. Our universal set U is the collection of whole numbers from 1 through 8. So our universe has 8 elements: 1, 2, 3, 4, 5, 6, 7, and 8. Conveniently, that matches exactly the 8 regions we need to fill. Set A contains 1, 2, 3, and 5. Set B contains 1, 2, 4, and 6. Set C contains 1, 3, 4, and 7. Now let's go through each element and figure out which region it belongs to by checking for each element whether it's in A, in B, and in C. The number 1. Is 1 in A? Yes. Is 1 in B? Yes. Is 1 in C? Yes. Code 111. The number 1 lives at the very center, inside all 3 sets. It belongs to A intersect B intersect C. The number 2. Is 2 in A? Yes. Is 2 in B? Yes. Is 2 in C? No. Code 110. The number 2 is inside A and B, but not C. It lives in the region where A and B overlap, but C is excluded. The number 3. Is 3 in A? Yes. Is 3 in B? No. Is 3 in C? Yes. Code 101. 3 is inside A and C, but not B. It lives in the region where A and C overlap, without B. The number 4. Is 4 in A? No. Is 4 in B? Yes. Is 4 in C? Yes. Code 011. 4 is inside B and C, but not A. It lives in the region where B and C overlap, without A. The number 5. Is 5 in A? Yes. Is 5 in B? No. Is 5 in C? No. Code 100. 5 is only inside A. It lives in the part of A that doesn't overlap with anything else. The number 6. Is 6 in A? No. Is 6 in B? Yes. Is 6 in C? No. Code 010. 6 is only inside B. It lives in the part of B that doesn't overlap with anything else. The number 7. Is 7 in A? No. Is 7 in B? No. Is 7 in C? Yes. Code 001. 7 is only inside C. It lives in the part of C that doesn't overlap with anything else. The number 8. Is 8 in A? No. Is 8 in B? No. Is 8 in C? No. Code 000. 8 doesn't belong to any of the 3 sets. It lives outside all 3 circles, in the outermost region of the rectangle. And there we have it. 8 elements, 8 distinct regions, each element occupying exactly 1 home. Every region is filled. Not a single one is empty. The partition is clean, complete, and perfect. Now I want to pause and address something important. The distinction that trips up many people when they first encounter Venn diagrams. We touched on it briefly at the beginning, but now that we've seen real examples with 2 and 3 sets, it's the perfect moment to revisit it carefully. The distinction is between a formal Venn diagram and an Euler diagram. Let's use a specific example to make the difference vivid. We have three sets. Set A contains 1, 2, and 3. Set B contains 2 and 4. Set C contains 5 and 6. Take a moment to notice something interesting here. Sets A and B share the element 2, so they do overlap with each other. But set C contains 5 and 6, and neither of those appears in A or B. So C is completely separate from both A and B. There is no element that belongs to C and also to A. There is no element that belongs to C and also to B. And there is certainly no element that belongs to all three. Now here's the key question. How do we draw this? An Euler diagram would draw the picture that reflects reality as simply as possible. A and B would overlap, because they share the element 2. But C would be drawn as a completely separate circle, floating on its own, not touching A or B. The diagram would only show the regions that actually contain elements. It would be clean, intuitive, and easy to read. But, and this is crucial, it would not be a formal Venn diagram because it skips the intersections that are empty. For instance, the region that would be inside A and C but not B. That region is empty, there's nothing there, so the Euler diagram simply doesn't draw it. A formal Venn diagram, on the other hand, is obligated to show all 2 to the power of 3, which is 8, regions, whether they contain elements or not. So in a formal Venn diagram, even though C doesn't actually share any elements with A or B, we must still draw C in a way that it overlaps with both A and B and with the intersection of A and B. The overlapping regions will exist as visible areas in the diagram, but they'll just be empty. No numbers live there. So in the formal version, all 3 circles still overlap one another in the traditional arrangement. And when we place the elements, 1 and 3 go into A only. 2 goes into the overlap of A and B. 4 goes into B only. 5 and 6 go into C only. All the intersection regions involving C are visibly present but empty. No elements, just empty space. The Euler diagram communicates the data more naturally. The formal Venn diagram is mathematically complete and rigorous. Neither is wrong. They serve different purposes. But now you know exactly what separates them, and you will never confuse the two again. We have come a long way together. We started with 1 set and 2 regions, then 2 sets and 4 regions, then 3 sets and 8 regions. And we've learned to carefully classify our diagrams, formal Venn versus Euler. In our next session, we'll take the leap to 4 sets, which brings 16 regions, and also a surprising geometric challenge that forces us to think beyond simple circles. It's one of the most fascinating twists in the entire story of Venn diagrams, and I cannot wait to show it to you. Rest up, and I'll see you there. Welcome back, and well done for making it this far. We've built our understanding carefully and patiently. 1 set, 2 sets, 3 sets. Each time, we doubled our regions. And each time, the same beautiful logic held. The binary codes worked. The truth table kept us honest. The partition was always perfect. Now we arrive at 4 sets. And I want to warn you, something surprising is about to happen. Something that will make you see Venn diagrams in a completely new light. Let's go. 4 sets. So n equals 4. And 2 to the power of 4 gives us 16 regions. 16 distinct areas, each one representing a unique combination of yes or no answers to 4 questions. Let's build the truth table. This time we have 4 sets, A, B, C, and D. For any element, we ask 4 questions. Is it in A? Is it in B? Is it in C? Is it in D? 4 questions, 4 answers, each a 1 or a 0. That gives us a 4-digit code for every region. Let's walk through all 16 rows, one at a time. Row 1, 0, 0, 0, 0. Outside all 4 sets, this is A, complement intersect, B complement, intersect, C complement, intersect D complement, nothing. Outside everything, row 2, 0, 0, 0, 1. Outside A, outside B, outside C but inside D. This is A, complement intersect, B complement intersect, C complement intersect D. Only inside D. Row 3, 0, 0, 1, 0. Outside A, outside B, inside C, outside D. This is A complement intersect, B complement intersect, C intersect D complement. Only inside C. Row 4, 0, 0, 1, 1. Outside A, outside B, inside C, inside D. This is A complement intersect B, complement intersect C, intersect D. inside C and D, but not A or B. Row 5, 0, 1, 0, 0. Outside A, inside B, outside C, outside D. This is A complement intersect B, intersect C, complement intersect D, complement. Only inside B. Row 6, 0, 1, 0, 1. Outside A, inside B, outside C, inside D. This is A complement intersect B, intersect C, complement intersect D. Inside B and D, but not A or C. Row 7, 0, 1, 1, 0. Outside A, inside B, inside C, outside D. This is A complement intersect B, intersect C, intersect D, complement. Inside B and C, but not A or D. Row 8, 0, 1, 1, 1. Outside A, inside B, inside C, inside D. This is A complement intersect B, intersect C, intersect D. Inside B, C, and D, but not A. Row 9, 1, 0, 0, 0. Inside A, outside B, outside C, outside D. This is A intersect B, complement intersect C, complement intersect D, complement. Only inside A. Row 10, 1, 0, 0, 1. Inside A, outside B, outside C, inside D. This is A intersect B, complement intersect C, complement intersect D. Inside A and D, but not B or C. Row 11, 1, 0, 1, 0. Inside A, outside B, inside C, outside D. This is A intersect B, complement, intersect C, intersect D, complement. Inside A and C, but not B or D. Row 12, 1, 0, 1, 1. Inside A, outside B, inside C, inside D. This is A intersect B, complement intersect D, C intersect D. Inside A, C, and D, but not B. Row 13, 1, 1, 0, 0. Inside A, inside B, outside C, outside D. This is A intersect B, intersect C, complement, intersect D, complement. Inside A and B, but not C or D. Row 14, 1, 1, 0, 1. Inside A, inside B, outside C, inside D. This is A intersect B, intersect C, complement, intersect D. Inside A, B, and D, but not C. Row 15, 1, 1, 1, 0. Inside A, inside B, inside C, outside D. This A intersect B, intersect C, intersect D. Complement. Inside A, B, and C, but not D. Row 16, 1, 1, 1, 1. Inside all four sets. This is A intersect B, intersect C, intersect D. The very center. All four. Every question answered yes. 16 rows, 16 regions. Every possible 4-digit binary code, from 0000 all the way to 1111, appears exactly once. The truth table is complete. Now here is the surprise I promised you. We need to physically draw a diagram that shows all 16 of these regions as distinct, visible areas. And here is the problem. We cannot do it with 4 circles. Think about it carefully. When we had 2 circles, they created 4 regions. When we had 3 circles, they created 8 regions. So surely 4 circles would give us 16. Unfortunately, no. 4 circles in a plane can create at most 14 regions. No matter how you arrange 4 circles, no matter how you tilt them, shift them, or overlap them, you simply cannot get all 16 distinct regions to appear simultaneously using circular shapes alone. This is a genuine geometric limitation. Circles are round. Their boundaries curve in a very constrained way, and that constraint, when pushed to 4 sets, falls just short of what we need. So what do? We abandon circles. We use a different kind of curve, a more flexible, irregular shape that can twist and bend in ways a circle cannot. By using these alternative curve-based shapes, we can construct a valid 4-set Venn diagram that genuinely shows all 16 regions, each one distinct and physically present. And the result is a diagram that looks quite different from the classic 3-circle picture you may be used to. It's a little more unusual in its shape, but mathematically, it is perfectly valid. Every single one of the 16 binary patterns from 0000 to 1111 appears exactly once and is physically visible as a non-empty region in the drawing. This is one of the most beautiful and humbling facts about Venn diagrams, that geometry itself imposes limits, and mathematicians have to get creative to work around them. Now let's make all 16 regions concrete, as we always do, with a real numerical example. Our universal set U is the collection of whole numbers from 1 through 16. 16 numbers, which is wonderfully fitting since we have exactly 16 regions to fill. Let's define our four sets very deliberately. Set A contains 9, 10, 11, 12, 13, 14, 15, and 16. That is the upper half of our universe. Set B contains 5, 6, 7, 8, 13, 14, 15, and 16. Set C contains 3, 4, 7, 8, 11, 12, 15, and 16. Set D contains 2, 4, 6, 8, 10, 12, 14, and 16. Notice that D contains all the even numbers in our universe. Now let's trace through the elements. I'll work through them in order, from 1 to 16, and for each number, I'll check all four set memberships. The number 1. In A, no. In B, no. In C, no. In D, no. Code 0, 0, 0. 1 lives in the outermost region, outside everything. The number 2. In A, no. In B, no. In C, no. In D, yes. It's even. Code 0001. 2 belongs only to D. The number 3. In A, no. In B, no. In C, yes. In D, no. It's odd. Code 0010. 3 belongs only to C. The number 4. In A, no. In B, no. In C, yes. In D, yes, even. Code 0011. 4 belongs to C and D, but not A or B. The number 5. In A, no. In B, yes. In C, no. In D, no. Odd. Code 0100. 5 belongs only to B. The number 6. In A, no. In B, yes. In C, no. In D, yes. Even. Code 0101. 6 belongs to B and D, but not A or C. The number 7. In A, no. In B, yes. In C, yes. In D, no. Odd. Code 0110. 7 belongs to B and C, but not A or D. The number 8. In A, no. In B, yes. In C, yes. In D, yes, even. Code 0111. 8 belongs to B, C, and D, but not A. The number 9. In A, yes. In B, no. In C, no. In D, no. Odd. Code 1000. 9 belongs only to A. The number 10. In A, yes. In B, no. In C, no. In D, yes. Even. Code 1001. 10 belongs to A and D, but not B or C. The number 11. In A, yes. In B, no. In C, yes. In D, no. Odd. Code 1010. 11 belongs to A and C, but not B or D. The number 12. In A, yes. In B, no. In C, yes. In D, yes. Even. Code 1011. 12 belongs to A, C, and D, but not B. The number 13. In A, yes. In B, yes. In C, no. In D, no. Odd. Code 1100. 13 belongs to A and B, but not C or D. The number 14. In A? Yes. In B? Yes. In C? No. In D? Yes, even. Code 1101. 14 belongs to A, B, and D, but not C. The number 15. In A? Yes. In B? Yes. In C? Yes. In D? No. Odd. Code 1110. 15 belongs to A, B, and C, but not D. The number 16. In A? Yes. In B? Yes. In C? Yes. In D? Yes. Even. Code 1111. 16 belongs to all four sets. It lives at the very center of the diagram. 16 numbers. 16 distinct regions. Each number goes to exactly one home. Every region is occupied. The four-set Venn diagram is complete. Now, having built all of this mathematical foundation, the regions, the binary codes, the truth tables, the diagrams, I want to show you something wonderful. I want to show you that this is not just abstract mathematics. This structure appears in real life, in a concept many people find deeply meaningful. The concept is called Ikigai. It is a Japanese word, and it carries a profound meaning. It roughly translates as reason for being, or reason to wake up in the morning. It is the Japanese idea of one's ultimate life purpose, the thing that makes your existence feel whole and worthwhile. And here is what makes Ikigai so perfect as an example for us. The traditional way of visualizing Ikigai uses exactly 4 sets, which means it maps beautifully onto a 4-set Venn diagram with all 16 regions. The 4 sets in the Ikigai framework are: set A, what you love, the things that fill you with joy, passion, and energy. The activities that make time seem to disappear. Set B, what the world needs, the things that are genuinely valuable to other people and to society, the things that make a difference beyond yourself. Set C, what you can be paid for, the things that have real economic value, the skills or services that people or organizations will exchange money for. Set D, what you are good at, your genuine strengths and competencies, the things you do with skill and ease. In this model, the central region, where all 4 sets meet simultaneously, where the answer to all 4 questions is yes, is the region coded 1111. That is A intersect B intersect C intersect D. And in the Ikigai framework, that central region is the approximation of Ikigai itself, the rare and precious overlap of everything: love, need, payment, and skill. But what is equally fascinating, and what the 4-set Venn structure reveals so clearly, is that all the other regions are meaningful too. Each region describes a different life situation, a different kind of partial fulfillment. Let's explore the regions that have exactly 2 memberships, where you answer yes to exactly 2 of the 4 questions and no to the other 2. The region where you are good at something and paid for it, but you don't love it and the world doesn't particularly need it, that is called profession. Mathematically, it is A complement intersect B complement intersect C intersect D. You have a career. You make money. You are competent. But something feels hollow. There's no passion and no sense of larger purpose. The region where the world needs something and you are paid for it, but you don't love it and you're not especially good at it, that is called vocation. Mathematically, it is A complement intersect B intersect C intersect D complement. You are doing work that matters and that pays, but it doesn't set your heart alight, and you may always feel like you're struggling rather than thriving. The region where you love something and you are good at it, but the world doesn't need it and you can't be paid for it, that is called passion. Mathematically, it is A intersect B complement intersect C complement intersect D. You are talented at something you adore, but it doesn't translate into income or societal need, a beloved hobby that never becomes a livelihood. The region where you love something and the world needs it, but you can't be paid for it and you're not necessarily good at it, that is called mission. Mathematically, it is A intersect B intersect C complement intersect D complement. You feel called to something. You care deeply and the world genuinely benefits, but financial sustainability is absent, and you may struggle with inadequacy. And then there are 2 regions that don't have traditional names in the popular Ikigai model, but which the mathematics insists exist. The region where you love something and are paid for it, but the world doesn't need it and you're not especially good at it, that is a nameless region. Mathematically, A intersect B complement intersect C intersect D complement. Enjoyable and financially rewarding, but perhaps lacking depth or impact. And the region where the world needs something and you are good at it, but you don't love it and aren't paid for it. Also nameless, mathematically, A complement intersect B intersect C complement intersect D. Selfless and skilled, but neither joyful nor financially sustained. The fact that the mathematics produces these unnamed regions is itself a reminder of how honest and complete the Venn diagram is as a tool. Life contains these combinations too, even when our cultural vocabulary hasn't gotten around to naming them. Now let's look at the regions with exactly 3 memberships, where you answer yes to 3 of the 4 questions and no to just 1. These are the regions that come tantalizingly close to Ikigai, but fall just short in one dimension. The region where the world needs what you do, you can be paid for it, and you are good at it, but you don't love it. Mathematically, A complement intersect B intersect C intersect D. This is described as feeling comfortable, but with a persistent feeling of emptiness. You are successful by most external measures, but something is missing from inside. The region where you love what you do, you can be paid for it, and you are good at it, but the world doesn't particularly need it. Mathematically, A intersect B complement intersect C intersect D. This brings satisfaction, but can come with a nagging feeling of uselessness. A sense that your work, while personally fulfilling, isn't making the difference you wish it could. The region where you love what you do, the world needs it, and you are good at it, but you cannot be paid for it. Mathematically, A intersect B intersect C complement intersect D. This brings delight and a sense of fullness. You feel purposeful and skilled and passionate. But without financial sustainability, there is always anxiety, always precarity. No wealth to speak of. And the region where you love what you do, the world needs it, and you can be paid for it, but you are not truly good at it. Mathematically, A intersect B intersect C intersect D complement. This brings excitement and enthusiasm, but it also comes with a persistent sense of uncertainty, a feeling that you might be found out, that you are always working a little beyond your genuine competence. 4 near misses. 4 different flavors of an almost but not quite life, each one real and recognizable, each one occupying its own distinct region in the diagram. Just to remind ourselves of the 4 sets we are working with. Set A represents what you love. Set B represents what the world needs. Set C represents what you can be paid for. And Set D represents what you are good at. Now, for any activity, any skill, any pursuit in your life, you can ask 4 simple yes or no questions. Do I love it? Does the world need it? Can I be paid for it? Am I good at it? Each answer is either yes, which we represent as 1, or no, which we represent as 0. And because there are 4 questions, each with 2 possible answers, we get 2 raised to the power of 4, which is 16 possible combinations. Every single one of those 16 combinations describes a different kind of relationship a person can have with their work or their calling. Before we begin, there is one important note to keep in mind: the mathematical descriptions. The ones written in terms of sets and their complements and intersections, those are precise and rigorous. But the cultural labels, the names like passion, mission, vocation, profession, and Ikigai, those are interpretive. They are meaningful, they are illuminating, but they carry cultural weight that goes beyond pure mathematics. So please hold them with that awareness as we go through them together. Let us now go through all 16 combinations, one by one. I want you to really pause on each one and imagine what it might feel like to live there. The first combination is 0, 0, 0, 0. This means not in A, not in B, not in C, and not in D. In set language, this is the complement of A, intersected with the complement of B, intersected with the complement of C, intersected with the complement of D. In plain words, you do not love it, the world does not need it, you cannot be paid for it, and you are not good at it. This is simply labeled outside. None of the 4 qualities apply. This is the outermost region of our diagram, the space beyond all 4 sets. The second combination is 0, 0, 0, 1. Not in A, not in B, not in C, but in D. The set notation is complement of A, intersected with the complement of B, intersected with the complement of C, intersected with D. You are good at it, and only that. You have a skill, but there is no love for it, the world has no particular need for it in this context, and no one is paying you. The label here is simply good only. The third combination is 0, 0, 1, 0. Not in A, not in B, in C, not in D. Complement of A, intersected with the complement of B, intersected with C, intersected with the complement of D. You can be paid for it, and only that. You are earning money from it, but you do not love it, the world does not particularly need it, and interestingly, you are not even especially skilled at it. The label here is paid only. The fourth combination is 0, 0, 1, 1. Not in A, not in B, but in both C and D. Complement of A, intersected with the complement of B, intersected with C, intersected with D. You can be paid for it, and you are good at it, but you do not love it, and the world does not need it. This region has a name, profession. You are competent, you earn a living, but there is no deeper love or sense of purpose driving it, just skill and payment, quietly working together. The fifth combination is 0, 1, 0, 0. Not in A and B, not in C, not in D. Complement of A, intersected with B, intersected with the complement of C, intersected with the complement of D. The world needs it, and only that. You are not good at it, you are not being paid for it, and you do not love it. The label is needs only, a somewhat lonely region to occupy. The sixth combination is 0, 1, 0, 1. Not in A, in B, not in C, but in D. Complement of A, intersected with B, intersected with the complement of C, intersected with D. The world needs it, and you are good at it, but you do not love it, and there is no financial reward. This region is left unnamed in the traditional Ikigai model. It sits in a quiet, somewhat selfless space, contributing without love or payment. The seventh combination is 0, 1, 1, 0. Not in A, in B, in C, not in D. Complement of A, intersected with B, intersected with C, intersected with the complement of D. The world needs it, and you can be paid for it, but you do not love it, and you are not truly skilled at it. This is called a vocation. Think of it as work that serves the world and keeps you financially afloat, but without passion or natural ability behind it. The eighth combination is 0, 1, 1, 1. Not in A, but in B, in C, and in D. Complement of A, intersected with B, intersected with C, intersected with D. 3 out of 4. The world needs it. You are paid for it, you are good at it, but you do not love it. This is described as comfortable, but with a feeling of emptiness. You have almost everything, but that inner spark of love is missing, and it leaves a quiet hollow somewhere inside. Now we move into the second half of our table, the rows where A equals 1. This means that in all of these remaining combinations, you do love it. The ninth combination is 1, 0, 0, 0. In A, but not in B, not in C, not in D. A, intersected with the complement of B, intersected with the complement of C, intersected with the complement of D. You love it. And that is it. It is not needed by the world. It pays nothing, and you have not yet developed great skill in it. The label is love only. Pure, unaccompanied love. The 10th combination is 1, 0, 0, 1. In A and in D, but not in B or C. A, intersected with the complement of B, intersected with the complement of C, intersected with D. You love it, and you are good at it, but the world does not need it in this context, and no one is paying you for it. This is called passion, a beautiful, energizing place to be, deeply personal, but without the grounding of purpose or income. The 11th combination is 1, 0, 1, 0. In A and in C, but not in B or D. A, intersected with the complement of B, intersected with C, intersected with the complement of D. You love it, and you can be paid for it, but the world does not need it, and you are not genuinely skilled at it. This region is also unnamed in the traditional model. A curious and somewhat fragile position. The 12th combination is 1, 0, 1, 1. In A, C, and D, but not in B. A, intersected with the complement of B, intersected with C, intersected with D. You love it, you are paid for it, you are good at it, but the world does not need it. This is called satisfaction, but with a feeling of uselessness. You are flourishing personally, but a nagging sense lingers that your work is not truly making a difference. The 13th combination is 1, 1, 0, 0. In A and in B, but not in C or D. A, intersected with B, intersected with the complement of C, intersected with the complement of D. You love it, and the world needs it, but you are not being paid, and you are not yet particularly skilled. This is called a mission, driven by love and purpose, but lacking both the resources and the ability to fully realize it. The 14th combination is 1, 1, 0, 1. In A, B, and D, but not in C. A, intersected with B, intersected with the complement of C, intersected with D. You love it, the world needs it, and you are good at it, but there is no financial reward. This is delight and fullness, but no wealth. There is deep meaning and joy here, but material sustainability is missing. The 15th combination is 1, 1, 1, 0 in A, B, and C, but not in D. A intersected with B, intersected with C, intersected with the complement of D. You love it, the world needs it, you are being paid for it, but you are not yet truly good at it. This is described as excitement, but with a sense of uncertainty. The foundation is there, and the energy is there, but the mastery has not yet arrived. And finally, the 16th combination, the one we have been quietly building toward this entire time. 1, 1, 1, 1, in A, in B, in C, and in D. A intersected with B, intersected with C, intersected with D. You love it. The world needs it. You are paid for it, and you are good at it. All four, together, at once. This is Ikigai, the Ikigai Venn diagram. And now, let us look at everything we just discussed drawn out in a single, complete picture. Every one of those 16 combinations, every region we walked through in that truth table, is now mapped onto one 4-set Venn diagram right in front of us. The diagram shows 4 overlapping sets, and they are labeled for us clearly. Set A is for love. Set B is for what the world needs. Set C is for what you can be paid for. And set D is for what you are good at. These 4 sets are arranged in such a way that every one of the 16 possible membership patterns has its own distinct non-empty region. Not one of them is collapsed or hidden. Every combination is physically visible. And at the very center of the entire diagram, where all 4 sets converge, A, intersected with B, intersected with C, intersected with D, is Ikigai. The one region where every quality is present, all at once. Each region corresponds to one binary membership pattern in A, B, C, and D, and that is precisely what we have been doing all along, translating the abstract language of binary codes and set intersections into something profoundly human. 16 regions, 16 ways of being, and right at the center, the one that contains them all, Ikigai. That brings us to the end of our tutorial on Venn diagrams. Thank you so much for staying with me through all of it, from a single circle with 2 regions all the way to 16. I hope this has made the structure feel not just logical, but genuinely meaningful. Take care, and I will see you in the next one. I am so very grateful for your kind support. It truly means the world to me. Please consider liking, sharing, and subscribing to join our gentle community. And I would truly love to hear your wonderful thoughts in the comments below.